Hi, good morning, guys. So today's our first day of our last unit. I tried to show you our schedule a little bit yesterday, but maybe you weren't able to catch it too much when we were running our test.
Tony Flirt, can you please come to the office?
My goal, the rest of this week, I guess, looks like lesson today, tomorrow, and I'll apologize in advance. Like you can probably see, there's a million slides to this, so this is gonna be a long day. Probably same thing with tomorrow. We're doing a lab on Thursday.
All grade 9 students, please go to the library. All grade 9 students to the library. Attention staff, the internet is down right now. We are working on it. We'll let you know when you can do your job.
I'm gonna need to go home. Okay, so lesson today, lesson tomorrow, lab Thursday. That's kind of the rest of the week here. I can't remember whether we have a work day Friday or another lesson Friday. Anyways. In terms of other important dates, I think I pointed out, I think it was May 26th, we're going to be finished the curriculum for the year. There's only 6 lessons in this unit. It's still worth 30%. It's actually one of the larger units. This one in Electrochem are percentage-wise worth the most, but I've always been able to cover the content in only about 6 lessons. I find this one most kids think is the most challenging of all 4 units. It has a very, very healthy mix of both theory and math. We're going to revisit acids and bases, not today or tomorrow, but in a couple of days we're going to revisit acid bases, which means that you need to remember how to do a lot of the calculations you would have learned in grade 11, where you do things like calculate the pH. The printer's gone, by the way. I printed off notes for you guys, so there should be some in a pile there. Is there some on your on the desk there? I should have passed it a few. Or just do one from here. Dakota's got one for you. There you go. So we're going to redo acid-base calculations, doing things like negative log of a concentration. We still have to do things like calculating a standard solution. So that'd be where you use a mass divided by a molar mass divided by a volume, try to calculate a moles per liter. So there's going to be a lot of math involved, but there's also a really healthy amount of theory questions involved as well. So yeah, long units, but like short in terms of how many lessons there are, a wide variety of question types. My goal is to be done the unit test, I believe it was on June 2nd, which is the Thursday of like the week before diplomas start. If that makes sense. So I don't have let me put a calendar up in front of you. That way you can at least try to visualize this. I don't know if you guys can see that little calendar in the corner much. So today's the 10th. I'm hoping to be done all curriculum by that 26th right there. That's my hope. I'm also hoping then to be finished the year in terms of our final unit test the week after that on June 2nd. That's the plan. The last day of classes is not until the 16th. Okay. So what would then happen is the June 2nd would be your unit test. June 3rd is Flex Friday, which should just be a nice day to get everything caught up that you're not finished. The week after that is basically our main week of review. Okay. And I'm gonna do what I normally do, where I give you guys some practice diplomas to write, not for marks, but we'll do some practice diplomas. We'll do some study sessions as well in that time. The week after that, for those of you guys in grade 12, I believe you have a diploma on Monday the 13th, and I believe your other diploma is on Thursday the 16th. Okay. So those days right there are gonna be pretty busy if you're in grade 12. On Friday the 17th, I'm gonna give you guys your lab final. And so I mentioned this before, rather than me doing just one final exam, I'm going to split it up into, I'm going to give you one final lab to do. And then on Monday, then we'll do our actual written final. So I'll try to give you more information about that lab final a little closer to the day, but I think I've already talked to you about it. We're going to do a back titration of a Tums tablet. Have I talked with you guys about this before yet? Okay, well, let me do it again here, just so it's kind of in the back of your mind. This is actually a lab that I've done with high school kids before, but it's actually one that I'm stealing from a university book. But I think you guys can handle it, because you guys are...
Susan staff, please dial 103. Susan, dial 103.
You guys are probably one of the strongest group of lab students I've had, so I really want to see whether you guys can pull this off. And if it totally tanks, then we'll reassess that then, so please don't freak out. But the goal is to basically test and see whether a Tums tablet actually contains the amount of calcium carbonate inside that it claims it does. Most tablets are either going to be 500 milligrams, maybe 250 milligrams. It might actually be 1,000 milligrams, which is kind of dumb because that's a gram. But our goal is to figure out whether there's actually that much calcium carbonate inside the Tums tablet. So we're going to do what's called a back titration, where we're going to take some acid and we're going to over-titrate the Tums tablet, which is actually a base. And we're going to do that to the point where there's a little bit of extra acid left over. Does that make sense? We're not going to actually neutralize it. We're going to overly neutralize it to the point where the base actually becomes acidic. Then the extra acidic part that's left over, we're going to titrate that with a primary standard of sodium hydroxide. And then in doing a lot of calculations, hopefully we'll figure out whether the Tums tablet actually contains the amount prescribed or whether it doesn't. That kind of makes sense? So, I mean, you guys have done lots of titrations with me before. I'll walk you through the calculations. So that would be the goal on that Friday. Do a lab final worth 10% of your final grade. And then on Monday, we're going to do an in-class final, which is worth 20% of your grade. When I say 10 and 20%, though, I mean 10 and 20% of the mark that I can give you. Okay, so I can give you ultimately 70% of your final mark because your diploma is worth 30%. So how does it work here? Diploma is worth 30. I give you 70%. Of that 70%, 10% will be the lab final, 20% will be your written final. That makes sense? All right. Anyways, let's move on. Yeah, it's coming fast. Like, we are nearly done. So why don't we get started? Today's a long day. We'll have to take a break halfway through. Okay, I want to envision a scenario, and I've been thinking about this all morning. I wish I had more students. I don't think this is going to work if we actually got up and did this activity. Or do you guys want to get up and move? Would you rather sit or get up and move? You want to get up and move? Okay, let's do it. Everybody up. Okay, let's try this activity. I need people to be basically in this just general vicinity here. And I need, let's say, 5 volunteers to help out this bear here. Who wants to run? Maybe not run, but like walk at a pretty brisk pace.
I can do that.
Okay, 1. Can you get a few more? Please. 2. 3. Need one more.
Oh my god.
Okay, here we go. Okay.
Randy Bonnet, I need you to call 103, Randy.
Okay, so here's the scenario. We are all going to be molecules that are going to react. Okay, we are all reactants currently. And what's going to happen is if people react, we're going to send them outside of the room in order to be products. Does that make sense? So for example, we're all going to now be colliding with each other. We bump into each other. That's enough activation energy to get a reaction proceeding. And so some of the reactants are going to start turning into products. So if you guys just want to take a quick step outside the room, I'll talk a lot about you up in here. So we now have some reactants who have started turning into products. Does that make sense? And slowly over time, the rest of us should be turning into products as well. Okay? So ideally, if everybody turned into a product, lost the call now. Say one visual here. We've now all turned into products. Here's the problem that we might incur with them. Okay? Sometimes products don't stay as products. Sometimes after a while, the products turn into products, and then they start turning back into reactants. But then the reactants start turning back into products again.
Oh my gosh.
So now what we've got happening here is some people going both directions. Does that make sense? And so I'm a product, well, I'm going to turn back into a reactant, and then back again. Okay. And what we have is a term called equilibrium. You guys ever heard this phrase before in other places? Right, where we don't have what's called a static state. When we were sitting at our desks, you guys are very static. You're just all sitting there, right? But what actually occurs at a molecular level is that reactants turn into products, products turn back into reactants. And sometimes we don't notice this. Currently, if I were to ask you for like a percent yield, I would say that almost all of us have turned into products. And there's like one person kind of hiding back inside the room. And that's actually very normal, that there might be like not everything fully reacts. Does that make sense? And so that's what our goal to talk about today is the idea of how things are going to be going both directions. We're going to talk about a double-sided arrow. We've actually seen this before in the, what was it again? The electrochemistry table. You know how there's that arrow that goes both directions? That's actually a very common scenario. So here's come back in now. So with that kind of move around demonstration done here, let me start with my opening cartoon here. Imagine a scenario where you've got a flask, and this is really important, that flask is sealed. We'll talk about that in a second, why that's so important. But imagine that you have even just like, say, my water bottle right here. Same sort of concept. Is this just sitting there in a static state doing nothing? And the answer is actually no. There's actually more occurring than meets the eye. What's actually happening here is these reactants, if you want to call them that, are turning into products. They're evaporating and turning into gas molecules. But do they stay that way? Well, probably not, because what's going to happen in the next slide is those gas molecules will turn back into liquids, but then what's going to happen instead? Well, if these three right here turn back into liquids, three more are going to have to evaporate. When I was just outside the door there, as soon as I got everybody outside the door and I started heading back in, if you can almost imagine like a two-way flow of traffic, where three people enter the room, three people leave the room, three more enter the room, three more leave the room. You're always going to have this cycle happening. Does that make sense, that concept? That's equilibrium.
Please excuse yet another interruption. The internet is up and running. Please check and see that yours is.
Okay, so here's some words trying to describe the thing I was just talking about here. If you are static, you guys know that word, static? Static just means that you're not really moving, I guess, like the book is on the desk, right? But if there's a dynamic equilibrium, if you've heard that phrase before, that would be like, say, someone juggling. At any given moment, a juggler would probably have one ball in one of his hands and probably two balls in the air. And as soon as he's about to catch the next ball, he probably has to throw one in its place. Does that make sense? And so if you're ever to take a snapshot, if you're ever to look at what was occurring at one time, you'd probably see two balls in the air, one in his hand. If he keeps going a little bit further, pause again, you'd see two more balls in the air, one in his hand, but it would be a different ball in the air and a different ball in his hand every time. Does that make sense? Extrapolate that to the scenario of us going outside the classroom. If we had a two-way flow of reactants and products, where reactants are turning into products, but products turn back into reactants, back and forth and back and forth, if you ever just paused for a second, ideally you should see the same number inside the room and outside the room. And then if you let the reaction run a little bit longer, and then re-paused, you might still see 5 inside the room, 10 outside the room, but it would be a different 5. Does that make sense? Like I originally sent just 5 of you randomly outside the room first. Those 5 might be the first 5 to come back again, but it might not be those 5. It might be 5 other ones. So, okay, here's another key word here. It has to be a closed system, though. Do you guys know the words open, closed, and isolated? Quick review then. What's an open system? Matter and energy can go in and out. Yeah, I mean, things is a good word, but more specifically, it has to allow mass, matter, as well as the flow of energy. A closed system means that matter cannot go in and out, but energy can. Closed systems are about as good as we can do. An isolated system is purely hypothetical. It means that you'd be able to cut off the flow of energy. But laws of thermodynamics, if you've ever heard of these before, they dictate that energy will always flow from like a warm to a cold kind of system. And so long story short is you can't make a perfectly efficient system. You're always going to have slight inefficiencies. And so you can't probably make a purely isolated system. Okay. Well, you guys can read. Let's move on. Here's what I want to talk about today then. This concept of double-sided arrows, where many chemical equations, it's not just that A and B turn into C and D. Often what happens is C and D starts turning back into A and B, and A and B turns back into C and D. And it's almost like you can think of it as like highway traffic flow, where there's some stuff going left and there's some stuff going right. And so there's actually more occurring than meets the eye. Now, if you're ever to pause and take a snapshot of what's occurring, maybe you'd have, like, say, when you start, you'd have 100% of this and 0% of that. And then 5 minutes later, you'd have 80% of this and 20% of that. As more of this stuff turns there, maybe a few kind of come back the other way and change the other way. And then maybe 5 minutes later, then maybe it'd be 70% here and 30% here. And then maybe it'll eventually become 70, actually I gotta keep going down here. Let's go 65% to 35%. But then eventually it's gonna kind of slow down to the point where as this stuff turns into C and D, the rate at which C and D turns back into A and B is the exact same. And as soon as the rate at which the two reactions take place, we call them the forward reaction and the reverse reaction. As soon as they're taking place at the exact same speed, equilibrium is now reached. Let's not get up to do this, but let's imagine an analogy here where, let's say I send 5 kids out of the room, and then 4 come back. And then I send 4 kids out of the room, and 3 come back. And I send 3 kids out of the room, and 2 come back. So that one more time. 5 out of the room, then 4 turn back. 4 go back out of the room, 3 come back, and then 3 go out of the room, and 2 come back. How many kids are inside the room, and how many kids are outside the room? You guys figure out that puzzle? Or do we actually need to get up and do it? Okay, so we have 5 kids. 5 go out of the room. 4 come back inside. So how many kids are outside right now? 1 to 4. Well then, those 4 kids return into products, but then 3 come back. Then those 3 turn into products, but 2 come back. So what's the split now? Well, now there's 3 on the outside of the room, but 2 on the inside of the room. If you like my analogy, that means that 3 things have turned into products, and 2 have remained as reactants. But here's where equilibrium continues, though. Then let's say that 2 kids go out of the room, and 1 comes back. And then let's say for the last one, let's say that 1 kid comes out of the room, but 1 comes back. And 1 kid comes out of the room, and 1 comes back. Can you envision a scenario where there's 1 kid in the room, he leaves the room, one of those 4 kids comes back over here. Well, then he goes back in. A different one takes his place. That would be an equilibrium system where slowly over time, reactants have turned into products. But as the products turn back into reactants, eventually it ends up having like a reaction rate where it used to be 4 for 1, then 3 for 1, then 2 for 1. And then as soon as it's a 1 for 1 change, now we're officially at equilibrium because the rate at which they're passing each other is the same as each other. That makes sense? Let me see if I can diagram that again. I'm going to really do this a lot today, so I'm sorry if you get the concept, because this is a really big thing here. So I'll just pretend that's a barrier. Let's say we have all of these different molecules here. And some of them are going to start turning from reactants into products. So let's say that these 3 guys right here, they change from reactants into products. So slowly but surely our reactants are turning into products. Well, then later more reactants will turn into products. So here's some more reactants turning into products. And you might be tempted to think that perhaps these last 2 will also turn into products. And that's true, but often in an equilibrium system, what's going to happen is some of these guys as products are actually going to turn back into reactants. So as soon as those 3 turn into products, the original 3, maybe some of them are going to go back the other way. Okay, quick recap of what I did. I took 3 of these, turned them into 3 of these. And I took 3 more of these, turned them into 3 of these, but then I took 2 of them and sent them back. Is that at equilibrium if you do a 3 for 2 trade? And the answer is no. It's not at equilibrium until the rate of transfer across the barrier is even. So let's say that then I take, say I take 2 of these guys, bring them over here, but simultaneously as 2 of these ones come this way, let's say that 1 of these ones goes back the other way. Is that at equilibrium? Let's say not yet. But eventually, let's say that the amount of reactants turning into products equals the amount of products turning backwards. So as these these two right here try to turn into these ones, if at the same time two of these ones turn back, now we're at equilibrium. If I were to ever look at a snapshot in time, currently there would be 5 products for every 3 reactants. Now, which 5 products or which 3 reactants you're looking at is going to change, because the next time that like this reaction takes place, 2 of these guys turn into, say, 2 of these guys, but at the exact same time, 2 of these guys are turning back into 2 of those ones. I still have a nice 5-to-3 ratio. Now, in this example, by the way, I was just arbitrarily picking 5-to-3. But does that make sense? Okay, let me move on. Hopefully it does. Okay. Again, I'm just trying to hit on the concept of the idea of forward and reverse reactions. For the last 7 units of me teaching you chemistry, we've always worked under the assumption that reactants always just turn into products. But we've never talked about the fact that sometimes reactions can undo themselves and can go right back to where they started. Esters are actually a good example of that, actually. You know how we made esters about a week ago? One of the reasons why the esters worked is because we heated them up. As soon as we cool them back down, sometimes they actually return back into carboxylics and back into alcohols. And so as you take A and B, acid and your alcohol, it turned into your it turned into your ester. It's actually very possible for that ester to turn right back into the acid and alcohol as soon as it starts to cool back down again. So, okay, key word again though, it needs to be a closed system. Anyone want to take a stab as to why it has to be a closed system? Yeah, you know how we were doing that example where I was having you guys go in and out of the room? Well, our closed system is the fact that you're still within the confines of the school. What happens if I let a few of you go run out the back doors? Well, that's going to throw off our equilibrium system, isn't it? Because then a few of you will have, quote-unquote, escaped. Does that make sense? So it has to be under a closed system because you can't have matter all of a sudden leaving. Okay. Here are the main 3 types of equilibriums I need you to know about. The first one's actually the cartoon at the beginning of the lesson, phase equilibrium, where, like, say, liquids and gases are changing back and forth between each other. It does not look like my water bottle is doing anything, but it is. There's water vapor in the atmosphere inside the water bottle, and there's water on the bottom here. If I could zoom in on a microscopic level, I would see water molecules evaporating into gas. But just as much, I would see the gas turning back into water. Water would turn into gas, gas back to water. And there's a cycle happening that I'm not actually able to see. Because it's an equilibrium, the number of molecules going both directions should be the same. So for every 3 molecules that evaporate, 3 more should return back into water. Does that make sense? What happens if I take the lid off? Well, now for every 3 molecules that evaporate, can I guarantee that 3 more molecules are going to return back into water? Well, no, because they can escape. Does that make sense? And that's why slowly over time, if I leave the lid off of this thing, eventually the water level will drop because it's not at equilibrium, because as I'm sending things out, there's not something coming back to take its place. Seal it back up though. Now do those water vapor molecules have the ability to escape? Probably not. That's one type of system. You should also know about solubility equilibrium. Last year or semester when I taught you guys about, like, say, precipitates, you can imagine you've got all that precipitate unsoluble stuff in the bottom of, like, say, a beaker. What's actually occurring is your copper sulfate, this is made wrong, by the way, that shouldn't be a 2 there. Your copper 2 sulfate, it should be dissolving, but then other ones should be undissolving. There should actually be like a system where aqueous ions are forming solid stuff, but other solids are breaking up into aqueuses. Aqueous form solid, solid form aqueous. And again, so long as it happens at the same rate, now it's at equilibrium. The one we're going to focus on, though, is a chemical reaction equilibrium, where reactants and products will actually go back and forth. Okay? It's not actually always a one-way arrow. Do you guys know the word macroscopic? Okay, do you guys know the word microscopic? Okay, well, think opposite. So if microscopic is things that like you need a microscope to see to zoom in really close, macroscopic is like stuff that you can just see with the everyday eye. Does that make sense? So like all of us are macroscopic. I can see you. However, I cannot see a proton, so that's microscopic. Here is an animated picture I found that hopefully can help illustrate the same concept. The idea of, do you guys see how the red balls, as they're coming into the solid, for every one that goes in, a different one should be coming out. Does that make sense? Now, if one goes in and 2 come out, it's not equilibrium. If 3 go in and 4 come out, it's not equilibrium. But as soon as eventually it reaches that balance where the transfer happening both directions is equal to each other, then it's equilibrium. The important thing to remember here is that when you see like one of the balls going into the bottom, it's not that same one that's coming out. It's actually a different one that's coming out because they're changing places. Make sense? Another analogy I like is the idea of like, say, a highway. I found this screenshot somewhere. Here's the idea of maybe cars going down the highway like the QE2 in Calgary, right? It's at equilibrium if for every 1,000 cars that go this way, 1,000 cars come back that way. What would happen if the rate was not the same? What would happen if, say, 100 cars went this way and 80 cars came back? What would happen slowly over time? Where would everybody end up at? Everybody would be over this direction. Does that make sense? I mean, when you first start, if 100 go this way and 80 come back, well, then you'd have to say, well, then there's 20 here and 80 here. But if that same thing kept occurring, then if 80 went this way and 20 came back, then you'd have like sorry, I put that here. You guys get the concept though, right? I can keep going here, right? If the rate is not the same, eventually everything will turn into a reactant or everything will turn into a product. We need the rates to be the same as each other. So, yeah, we can move on. Here's a diagram of a very famous equilibrium system that I would love to do, but I don't have the stuff to do it. This is the equation for this one is actually on the next page. So maybe I'm going to flip back and forth between these two. Are they on the same pages for you guys, or are they over the page break? Oh, shoot, they're over the page break. Can you guys find this one here first? This is a very famous equilibrium system where what ends up happening is N2O4 turns into NO2. This is the equation. N2O4, which is normally colorless, will turn into NO2. Slowly over time, something that is colorless will turn into something that is kind of brown. But it actually is temperature dependent. If it's very, very cold, it'll actually stay in the colorless state. But as you add heat, you guys already know this, as you add heat, heat can cause a reaction to kind of speed up a little bit. Does that make sense? And in doing so, it pushes it so that rather than everything going this way, where most of it goes like this, and, oh, I did that wrong. Initially, a little bit of it turns like that, and most of it turns right back. Can you envision how, like, if you had this N2O4 and this NO2 as like a system here, if a little bit of it turned brown, but most of it turned right back to colorless, it would end up looking like this. Okay. However, if the rate was something different, if most of it was turning this way and a little bit turned back, that would be over here, where you mostly have NO2. However, the one in the middle is probably at equilibrium, where you have some N2O4 turning into NO2, but you have just as much of it turning right back the other way. And then you'd have kind of an in-between color, where here it's colorless because you have mostly this. Here it's brown because you have mostly this. But in between, if the rates are the exact same as each other, then you might actually have some colorless and some brown, and that makes it look like a pale brown. Does that make sense? Or if I use the slide before it, sorry that it's kind of out of order. Here, you have mostly just the colorless ones and like one of these brown ones. And what's going to happen is these guys will just keep changing place. This guy will turn into a white one, and one of the other white ones will turn back into a brown one. Whereas over here, you're actually having way more of the brown ones stay on the brown side as opposed to the white ones. So you can actually kind of tell where an equilibrium system is at for this very famous one based on how much color there is to it. More pictures. So here's a system where you started off with mostly these guys right here, and slowly over time, all of a sudden now you have 3, then you have 5, then you have 1, 2, 3, 4, 5, 6, 7. Slowly over time, it looks like from reactants to products, it looks like the arrow is mostly towards the products and not so much towards the reactants because we're gaining more products over time. Does that make sense? Now, it's the same thing in all of these reaction systems, but they're a little bit slower, wouldn't you agree? Like if you compare this system here to this one here gained 3, here it gained 2 more, here it gained 2 more. Well, this one just gained 1, this one just gained 2, this one went from 1 to 2 to 3. This one's a little bit slower, so I might suggest that the reactants to products for this one is more like that. Does that make sense? Where you're slightly making more products than are turning back to the reactants. This one right here is much more heavily favored towards the products. When we do chemical equations like this, we've actually learned this before, but we had a different word for it. We called it this. So after all of this talk for the last 45 minutes here, what I'm actually talking about is a percent yield. If you have a high percent yield, what does that mean about the 2 equations, the forward and the reverse equation? If you have a high percent yield, which one dominates? The forward percent would be very much dominating if you have a high percent yield. Right? This one right here, I might suggest that it's like a 90-10 split. Does that make sense? Where like 90% of what I'm creating is products. If I let this continue over time, will I still have a few of these blue and purple boxes left over? Yeah, I might have like a few of them left over. But ideally in this system right here, it's being pushed very heavily towards the products, where I might call this like an 80% yield. Does that make sense? But this one down here is nowhere near as strong. Yeah, we're trying to take the blue and purple boxes and turn them into orange ovals. But here the percent yield might be more like a 20% yield. Because yeah, we're trying to turn this stuff into this, but as we're trying to, it looks like it might be turning back into the original pieces it started with. So in a way, an equilibrium system is very highly tied to percent yield because it will tell you at what rate the 2 equations are occurring. For it to be at equilibrium, we need it to happen so that the 2 reaction rates are actually the same as each other. Okay, so summary here then. If it's at equilibrium, it has to be closed. So for our purposes, by the way, a test tube or beaker is a closed system as long as there's no gases. Okay. If gases are involved, you have to put a lid on something. But if it's just solids and liquids, we can just put it in a beaker. That's usually good enough. Okay. I guess here's another analogy. Boy, I'm sorry if like you get this and I'm just beating a horse to death here, but I really want to make sure you get this concept. Here's an analogy. Is this first system here at equilibrium? Yeah, it's balanced. Does that make sense? These 2 people are equal to each other. Here, your products are more heavily weighted than your reactants. So this is a reaction which is going to heavily lean towards your products. It would have a high percent yield. Here is one where it's actually back to being the first one again, though. Eventually, it might level out again. And so you might have created a lot of products, but now you've got a nice balance again in this particular one. Okay, why don't you guys take a break? Now that I've covered the theory, now we got to talk about the math behind it. So why don't you guys take 5, though, because I've still got more to cover. Okay, so before I get to the math problems, just one more visual to hopefully help tie this equilibrium concept together. Sometimes, no, not sometimes, you're probably going to get a graph on the diploma. And it might look something like this. On one axis, they're going to put time, and on the other axis, they're going to put reaction rate. Okay, reaction rate is really referring to like how fast each reaction is. So if I happen to have one reaction going that fast and one going this fast, are we at equilibrium? No. But if they're going at the same speed at each other, so if like 5 people leave and 5 come back, then it's equilibrium. If 5 leave and 4 comes back, it's not equilibrium. Okay. Well, in terms of a graph, the reason why this is at equilibrium is because these two lines are now touching each other. It's not at equilibrium. This is really important. It's not at equilibrium because it's directly like half. Okay? Equal does not necessarily mean that you have to have the same amount of products as reactants. Because if you had the same amount of products as reactants, you would have a 50% yield. But that's not equilibrium. Equilibrium is when they're transferring back and forth. They're equal. That's when it's in equilibrium. Let me show you a couple other graphs maybe. Let's say that you had a graph like this where here was the reverse reaction. And here was the forward reaction. Do you see how they did not meet like right dead center in the middle? What might the percent yield for this reaction be then? You want to hazard a guess? 80, 90%. The reason why is that your forward reaction and your reverse reaction, your forward reaction was basically strong almost the whole way through. And it took a very long time for your reverse reaction to catch up. Does that make sense? And because of that, if you can imagine a scenario where you've got, like, say, 100 inside the room, 80 of them go out, 20 come back. 80 of them go out, 20 come back. 70 go out, 30 come back. 40 go out, 30 come back. 35 go out, 35 come back. 35 go out, 35 come back. Now I'm finally at a nice balance. Does that make sense? The reason I'm at balance is because I said 35 go out, 35 come back. But because so much stuff has left the room before the balance occurred, it means your percent yield is very high. That makes sense? You could ultimately have a graph that looks like this as well, where here's the forward reaction rate, and it might drop like this, and here's your reverse reaction rate like this. I might suggest that your percent yield here might be more like 10%, where the first time you do this, 100 leave the room, and then maybe 90 come back. So then you'd have like a 90 to 10 split. And then maybe you'd have 80 leave the room and 75 come back. So then you'd have 15 out here and 85 out there. Does that make sense? And maybe you'd reach the point where 15 go out and 15 come back. Well, then nothing would change. And then 15 go out and 15 come back. Nothing would change.
Okay, so just to make sure I'm understanding properly.
Yeah.
An equilibrium is when one thing goes out and the other one comes back in
Yeah.
the same amount.
Yeah.
But it's not the same amount on each side.
Yeah.
Okay.
Does that make sense?
Yeah. Just double checking.
No, that's good. I mean, if you guys would be okay, I would love to do another visual. But if you feel like you got the hang of it, I can move on. Because like we can use people to try to describe equilibrium. Do you guys feel like you have the hang of it? Okay. If you don't, come find me later. I'll try to get manipulatives to make it work. But the next thing I need to do then is we need to do some math behind this. Okay. So the very first thing we can do is a percent yield. You guys remember how to do percent yields. It's what it actually should be divided by, in theory, how much it could have been. Like what is the most you could have made times by 100. Okay. The other thing we can do is we can try to figure out basically the position of equilibrium. You guys remember the word non-spontaneous from the electrochem unit? Well, that would be in the example of here we all are as reactants wanting to leave the room. If I just don't let anybody leave the room, then it's non-spontaneous. It means you have a 0% yield because literally nothing happens. Does that make sense? All the way up to the point where you have reactants favored, where there's like more reactants than products. Then you could have products favored, where you have more products than reactants. Or you could have something that's not really considered at equilibrium anymore. You have something called quantitative. And this is where basically 100% of the stuff actually reacts. So you know when we did our little example and we all left the room? That would have been quantitative because literally everybody left the room. As soon as I started having people come back inside the room going back the other way, then it's still at equilibrium at least. But if just everything reacts and nothing turns back the other way and goes back to a reactant, then it's considered quantitative. So. Okay, let's fast forward to our example. So this is a really common kind of question you're going to have to solve. And I think it's best if I just solve one first. So we use something called an ICE table. ICE stands for initial, change, and then equilibrium. Initial for I, change for C, and E is equilibrium. Okay. And so let me just solve one first. Just watch, I guess. So what we're going to do is we're going to form hydrogen iodide from its elements. Well, the first place I'd start is by saying, well, to form hydrogen iodide, we need to create HI, probably a gas, and we're going to form it from hydrogen and iodide. I'll guess that it's a gas as well. So there's the chemical equation. The problem that we're going to have, though, is that as soon as hydrogen and iodide start forming hydrogen iodide, it may actually start returning to its elemental state and recreate hydrogen and iodide in its like elemental forms. And so currently, as I've drawn this arrow, it looks like mostly over time it's going to turn into hydrogen iodide. But eventually, this arrow here is going to grow and grow and grow. And eventually, at some point, the rates will be equal to each other. Does that make sense? And the reaction will have essentially slowed down and you won't see any change. So what we normally do then is throw I, C, and E off to the side here, and we try to calculate how much initial concentration they have, how much final equilibrium concentration they have, and then what it took to change to get there. So based on this, it says that the initial concentrations of hydrogen and iodide were 1 mole per liter. So that means that up here, this hydrogen initially was 1 mole per liter, and this one right here was 1 mole per liter. How much hydrogen iodide would we have started with, though? Anyone want to take a guess as to how much should go right here in this column? None. Because we didn't have any. We're trying to make hydrogen iodide at first. Does that make sense? In the example of us leaving the classroom, how many of you were outside the classroom when I started that activity? None of you were, right? Slowly over time, though, a few of us ended up outside the classroom, right? Therefore being products. So originally we started with 1 mole per liter of each of these two, and there was literally nothing here. Now imagine that for like a split moment in time, Forster walked up and said, "Schulk, what the heck are you guys doing?" And as he looks at us, he discovers that there are 0.22 iodides left back in the classroom. So imagine he walks in the back door, looks in the classroom and goes, "Where the heck is everybody? You're supposed to have 100% of kids and you've only got 22% of them left." Right? How do you get from 1.00 down to 0.22? How much change would have had to have occurred? Well, it must have gone down, right? By how much? Yeah, 0.78. That makes sense? This one right here, this one right here, and this one right here, they were all given to us. They were all stated in the question. This is who was in the classroom when we started. 10 minutes later, Forster wanders by and notices that there's only 0.22 kids left in the classroom. Where the heck did everybody else go? Well, it's because some kids were standing in the halls. Our goal now is to fill out the rest of this chart. Well, according to this equation here, we need to do one more thing. I didn't balance it. In order to balance it, you need a 1 right here, a 1 right here, and here's the real key. This is a 2 right here in order to balance. Well, based on that information, if this guy went down by 0.78, I actually know what this column right here is going to be as well. Because both of these reactants are going to lose the exact same amount. They're both going to lose 0.78. If the reactants are going down, though, the products have to go up. Does that make sense? Like, it's not possible to have negative products, so this has to go up. Well, the amount that it goes up by is this amount. Why? Because of the 2 right here. It's this 2 right here. Okay, it's not the fact that both of these add together. It's the fact that for every one of these and for every one of these, you make 2 of these guys. That makes sense? So therefore, its concentration will actually be doubled as well. Well, now I want to finish off the rest of the table. Almost need to think of it as though there's a line right here. 1 minus 0.78 gives you 0.22. Well, what happens right here? 1 minus 0.8 gives you 0.22. What is 0 plus 1.56? 1.56. So if this was the analogy of us starting in the classroom here, are there more products or reactants now? Is this something that more favored the reactants or favored the products? Products is correct. Yeah. Pretty heavily, actually, right? What ended up happening is lots of stuff left. And then slowly but surely, some started coming back the other way. But the problem is, so much stuff had left and turned into reactants that as those reaction rates finally stabilize and normalize and steady each other, almost everything has actually left the room and has become a product. Does that make sense? There still is some reactant left, but most of it's turned into this stuff right here. Now, what I'd like for us to now do is calculate a percent yield. Well, the formula for percent yield is what did you actually make divided by how much could you have theoretically made? Theoretical times by 100. How much did we actually make? Well, we started with nothing, right? We went up by 156, so we've made 156. Does that make sense? This number right here is what we actually produced. There are now 1.56 moles per liter of hydrogen iodide. That's how much actually was made. How much could have been made if everything reacted? Because clearly I still have some reactants over here on the wrong side. 2 moles per liter, yeah, that's actually the right answer. It's 2 moles per liter. Now, I want to explain why it's 2 moles per liter, though. It's not because it's this plus this plus this, although that does work. It's actually for a different reason. If you had 1 mole per liter, see how there's a 1 right here? And there's a 2 right here. 1 mole per liter could have doubled to become 2 moles per liter. Just similarly, this 1 mole per liter, with a 1 right here, could have doubled to become 2 moles per liter. Neither of these two things is actually in excess or limiting. Because they were like the exact same proportions, we don't have an excess or limiting reactant. So based on this, 1 could have doubled to as much as 2. This 1 could have doubled to as much as 2. So the most you could have made would have been 2. So then if you divide these two things, I think it's about 78%, give or take. 77%? 156 divided by 2? 78. Memorized it from last year. So long story short, we have now created an equilibrium system where this is not 50%. Equilibrium does not mean you have half reactants, half products. What it means is that the rate of reaction, the reactants usually turn into products fast, but eventually the products will turn back into reactants. As soon as that rate of flow, like think of two sides of a highway, as soon as that equalizes, then we're at equilibrium. All right, that makes sense for the first example. Okay, let's try another one. I lost my little arrow thing. By the way, here's a graph just to kind of illustrate sort of the concept here. Now, this one's kind of unfair to compare. Know how I did one earlier where they were coming up like that and they were meeting in the middle? This one's a little bit unfair to compare just because there's actually 2 reactants and 1 product. So they don't necessarily meet in the middle, but do you see how like the amount, the quantity is leveling off? As soon as the quantity is leveling off, now we're at equilibrium because you're not making any more hydrogen iodide. The amount that's being made is actually stabilizing. Okay, let's try another example here. We're actually going to do the exact same equation. We're going to do the hydrogen iodide one again here. So the first thing I'm going to do is I'm going to write out the equation. We've got hydrogen iodide placed in a vessel, and it's actually going to turn back into hydrogen gas and iodide gas. So the first thing I'm going to want to do is write out the equation. HI is actually going to decompose back into H2 and I2.
There you go.
Like this. Then I want to start filling out some of the numbers as to where I can put them. It says that originally there was 0.463 moles of hydrogen iodide placed there. Where would that 0.463 number go? Yeah, it would go there. Now it doesn't say as much, but it actually implies as to what numbers go here and here. 0. Because we didn't start with any of that stuff. Unless it happens to say that we started with some. Okay, well then it gives you some information that's really not relevant, like the 1 liter reaction vessel, that wasn't relevant. The 300 degrees Celsius, also not really relevant. But then it tells you that at equilibrium, Forster walks in the room and wonders, why is not everybody in the room? Why are some people missing, right? Well, it's because you have 0.119 of hydrogen and 0.119 of iodide. So at equilibrium, you had 0.119 of hydrogen, and you also had 0.119 of iodide. So that was the information we were given to start with. I like to suggest to kids it's kind of like a Sudoku. You guys ever do Sudokus where you have to like kind of fill in like the middle number and then it helps you to solve for the next one over and that helps you with this one? It's like a puzzle. Because what I could say is, how in the world do I get from 0 to 119? Well, it means that this must have gone up by 119. This one must have also gone up by 119. Well, that means this one must have gone down. But it didn't go down by 119 because I haven't balanced this. For every 1 iodide I make, I also make 1 hydrogen, but I require 2 hydrogen iodides. What number should go here then? Do you have any idea? Well, if this one goes up by 119 with a 1 right here, this one's also a 1 that goes up by 119. This one's got to go down by double that. So what happens when you double 119? 238. So this one's got to go down by 238. The rationale is this guy right here and this guy right here, they each have 1s attached to them. So then this one right here has to be doubled it. Okay, so then, can someone help me out here? What's 463 minus 238? There, now we know where everything has ended up at. Now for the harder question. What's our percent yield? Okay, well, to figure out the percent yield, figure out what you actually made. I don't think it really matters which one of these two we pick, but how much iodide did we make? We made 119 moles per liter. That makes sense? That's how much we actually made. How much could we have made? Okay, well, it's actually this number right here we need to focus on. You see how you got 463 right here? Well, it comes in a group of 2. The iodide would have been half of that. Does that make sense? So if all of your 463 had reacted and not had a little bit left over here, but if all of the 463 had reacted, the number that could have been over on this side right here would be half of 463. So what's 463 divided by 2? That'd be 2. Shoot, I can't do math. What's 462 divided by 2? Like that. That's how much could have reacted, because this number right here could have been cut in half to make half of it into this, half of it into this, and then this guy would have had nothing left. So then we divide these two guys. This one's just under, like about 50% or so, right? 51%. So I would say this one slightly favored the products. By the time the reaction rates finally slowed down enough, we had just slightly more products than reactants. That makes sense? Okay, let's try another example. It's a lot at first, by the way. Please don't freak out if you're like, it's going over your head a little bit. It takes a while to kind of sink in. You got to do quite a few examples. Let's try another one. It says we're going to establish equilibrium when bromine monochloride decomposes to form elements. Okay, well that equation would be this. Here's bromine monochloride. If it decomposes to form elements, its elements would be bromine gas and chlorine gas. I'm going to guess gases. Think of it like a puzzle. What information can you slot into this like tic-tac-toe kind of puzzle? Well, you were given one number right off the bat here, this 337 number. Where would this 337 number go? Yeah, the I for bromine chloride. So that's 0.337 moles per liter. Okay, well then it says that the equilibrium concentration of chlorine gas is 0.0215. Where would this number right here go? At equilibrium, chlorine gas is 0.0215 mole per liter. There's actually two more numbers that we can throw in somewhere that weren't stated in the question, but that we should be able to assume that are, yeah, we should be able to assume that if we started with 337 of bromine monochloride, that we didn't start with any of this. Again, think of the example I tried to do with you guys where we were getting up and walking, right? How many of you started the classroom on the outside of the classroom? Like when I started that activity, no one was outside the room, right? So, well, how do you get from 0 down to 0.215? Well, in the change column, this guy must have gone up by 0.0215. The change column is the key, by the way, because the change has to occur according to the ratios. And so far I'm picking very boring examples because they all have like 1 to 1 to 2 ratios. We'll do different ones in a bit. But if this is a 1 and this one goes up by 215, should this one go up by like 317? Would it make sense for this one to go up by a different amount than this one would? That doesn't seem logical, does it, right? I mean, because these two things right here, they have 1s. So this guy should also go up by 0.0215. Well, how are these bromines and chlorines able to go up? Well, it's because this one went down. How much does it go down by? Well, if this is a 1 and this was a 1 and that one's a 2, then this has to be going down by double as much because half of it went to each. So this is 0.0430 moles per liter. So for the last step then, kind of fill out the rest of the table. 0 plus 0.00215 is just the 215 number. What is 337 minus that 430? Anyone have that? 0.291? 94, thank you. By the time this equilibrium set in, did we manage to make much bromine and chlorine by the time the equilibrium finally caught up? I'd say no. So if you like the analogy again of like leaving and coming back into the room, it's like I sent 5 kids out of the room, but 4 came back. And then I sent 4 kids out of the room and 3 came back. And then I sent 3 kids out of the room and 3 came back. And I sent 3 kids out of the room and 3 came back. And at this point now, well, now there's no change happening. So really the net is that like a few kids made it on the other side, but pretty much now as transfers happen back and forth, there's really nothing happening all that much. So for the last step, we want to try to figure out a percent yield now. So how much did we actually make? I don't think it really matters on which one we do. But in either case, we actually made 0.0215 moles per liter. This is the hardest one for most kids to figure out. How much could we have made? How'd you find that? Good, yeah, that's exactly what you do. You take the original number and say, well, of this stuff right here, if this is a 2 and that's a 1, then half of it should have turned into bromine, and the other half should have turned into chlorine. So what did you get? 0.1... Say it again?
685.
Yeah, 685. That's how much we could have made for each of these two things right here. Times it by 100, that's your percent yield, which is probably pretty low. How much? 12.7.
Or 12.8.
So in this example here, by the time that the equilibrium kind of caught up so the reaction rates were similar, not really much had actually transferred from one side back to the other one. Okay, there's 3 ice tables. Give me a thumbs up down in the middle just so I can kind of gauge as to how well you feel about this. Okay. Ish for many of you, and some are okay. Okay, this is the sort of thing where please don't freak out after an hour if you haven't picked up on this, because it takes a while to kind of do some practice on this. So I will try to make sure I do some more practice with people who need them. Okay. Unfortunately, I'm still not done. Sorry. There's one more thing I want to do, and this is called the equilibrium constant law. Percent yield is a very useful way of trying to calculate whether a reaction tends to be progressive and favor products, or whether it kind of gets stopped in its tracks and mostly favors the reactants. But there is another method, and it's called this K_C. It's called the equilibrium constant. In order to calculate it, this is another one of those things where you're going to have to bear with me and let me try a few examples first. Here's the formula for it. To find this constant, what you do is you take your products, you find their concentrations, and that's what the square brackets are for. Square brackets means find their concentrations in moles per liter, but then times them to the power of whatever the coefficient is in front. So if there is a 2 or a 3 or a 4 as like a coefficient, you have to square or cube. And then you divide by the reactants, doing the same sort of thing. What I'd like to do here is go back to the last example we did, and I want to calculate what's called a Kc value. And then after I calculate it, I'll talk a bit more about how it's useful. So, if I want to calculate a Kc value, the way it works is you take your products and you times them to the power of like an exponent, and you take your reactants and you also times them to the power of exponents. What are my 2 products? Well, my 2 products in this example were bromine. What was the coefficient in front of bromine?
1.
And then chlorine. What was the coefficient in front of chlorine? 1. Yeah. And then on the bottom, I need to know what my reactant was. And my reactant was that bromine monochloride. But what was the coefficient in front of that one? So you put a little 2 up in the corner. Now, the way this Kc value works is it's an equilibrium constant. So we have to put the equilibrium concentrations in once an equilibrium has been reached. So what was the concentration of bromine at equilibrium? This is 0.0215. What was the concentration of chlorine? Also 0.0215. What was the concentration of bromine monochloride at equilibrium? This number right here, the 294. By the time it was done, there were still 294 left that hadn't reacted. But I have to do one more thing, though. This number has to be squared. So to find what's called an equilibrium constant, you would do 0.0215 times by 0.0215. Then you divide by 0.294. But that 294 number gets squared. And this gives you what's known as an equilibrium constant, which would be 0.00534788 or something like that. We still do sig digs, so looks like you get 3 sig digs. Okay, context time now. So you probably have some questions. I'm guessing you probably were able to follow that and go, okay, I can plug some numbers in a formula. Probably the biggest question you'd have is, why? And here's where this kind of sucks. I have really good reasons. I promise you. We're not ready to like bite off that much of the apple yet, if that makes sense. So what I really want to do right now, if it's okay with you guys, you really don't have much choice anyways, but if it's okay with you guys here. I want to show you how to do KC calculations. And then over the next couple of lessons, we're going to talk about why they're relevant and what they can accomplish. Does that make sense? But we haven't gotten that far yet. But what I can do is give you some Cliff Notes versions of what this number really refers to. Okay? This number is a measure, just like percent yield, of how much the reaction has actually turned into products versus stated reactants. If this number is a very small number, it means that you have a very low percent yield. And because this number is very tiny, we have a very low percent yield. If this KC value was large, like say 17, 18, 200, it means it would be very highly products favored. That's the one thing it can do. The other thing right now that we can do with this is we can compare two different reactions to each other. So what I'd like to do is I'd like to go back up and try the other reaction that we did a few minutes ago. Well, I erased mine. Shoot, that was dumb. Can you guys find this one right here? I want to do the exact same thing with this one right here, because we can do a comparison. That's the other reason why it's useful. So to calculate a KC value, the way it works is you take your products. What's my product in this one up here? You can still see it. This one right here, right? The 156. I'll just write it even out as the 156 here. And I have to go to the power of whatever exponent, like whatever coefficient it had. See how I did it 2? So I'm going to have to square it. Then I have to divide by my 2 reactants. What were my reactants? 0.22 and 0.22. Each of those, though, went to the power of 1. So that's the 1. That's 0.22 moles per liter to the power of 1. I got about 50.2. Okay, so again, you probably can do that. Because it's not hard to calculate a KC value once you've been shown a few of them. The question again is, how is it useful? Okay? Like I said, I promise, we'll work on that over the next few days. That's the whole point of what we're doing. But for right now, it means 2 things. One, the bigger the number, the more likely it is that you're forming products. You know how last time around the number was 0.00 something? We weren't forming many products, which made sense because on that slide over here, what was our percent yield? I had it as about 12%. A 12% yield meant that this number here was very small. Fair enough. But on the example I just tried a few slides back here, I had a 78% yield. This number right here is quite large. Essentially, the larger the KC value, the higher the yield. Does that make sense? The other reason why we use these, though, is because it's a comparison tool. We can now compare different reactions to each other and compare their KC values, as opposed to comparing their percent yields. Percent yields are nice, but each equation kind of has its own little nuances to it. A KC value is a very it's a good way of being able to say, well, here's one here, here's one here. Which one produces more? And since this is 50.2, it's higher. Let me go through some of the notes I had on the KC value here, because I'm sure I have some there. Here it is. If you ever have square brackets, it means you have to be in moles per liter. Here's a really important one. KC does not get a unit. You might have noticed that when I wrote down those numbers there of like 50.2 and whatever the other one was, I didn't put any units behind it. It's not like a percentage. It's not a moles per liter. It's just purely, it's a ranking number. We can actually use them to figure out which reactants are more likely to produce products than the other ones. If I gave you one reactant with a KC value of 100 and another one with a KC value of 7, which one is going to produce more products? That one's going to produce more products. Does that make sense? So that's what they're used for. Not only that, if KC is greater than 1, it's products favored. if your Kc is like 0.01, this is actually not products favored at all. This is reactants favored, where most stuff right here is not reacting at all. You're hardly producing anything. Okay, here's a really important point. This will come up eventually. It has to be either a gas or a dissolved state. And by dissolved state, that pretty much means for us aqueous. The reason why is it has to have a variable concentration. Concentrations have to be able to change. If your concentration cannot change, then how do you make an ice table if one of the columns is for change? Does that make sense? You can change the concentration of a gas. You can change the concentration of an aqueous. You cannot change concentrations of solids and liquids. With one exception. We still do this if everything is a liquid. If everything is a liquid, we can actually still pull this off. Okay, let's try a few more examples here and then I'll wrap it up for the day here. Let's try to write this equilibrium law expression for nitrogen monoxide and oxygen forming nitrogen dioxide. So the first thing I want to do is write an equation. What's nitrogen monoxide? NO. What's oxygen gas? O2. What's nitrogen dioxide? Perfect. Okay, before I go any further, I need to make sure I balance this thing. This is the first one we've done today that doesn't have like 1s and 2s everywhere. This one's a little bit different. Well, at least it's not 1 + 1 = 2. Does that do it? Okay, well then if I want to write the equilibrium law expression, here's what you'd do. You would take whatever your NO2 concentration is, you'd square that, and you would divide by whatever your NO concentration is. You'd also square that. But you'd also have your oxygen concentration, but you'd only use one of those. This is called the equilibrium law concentration kind of formula. If this number ended up being a number like, say, 50 or 60 or something like that, it means it's product favored. It means you're making a lot of products if the Kc value is high. If the value is like 0.001 or 0.05, it means that the reaction does not actually produce very much. And so those Kc values can be used to predict whether or not a reaction is actually going to be useful to you. That makes sense? Let's try another one. Let's decompose ammonium chloride into ammonia and gaseous ACl. What's ammonium chloride? Ammonium is NH4, Cl. What is ammonia? NH3, yeah. And we need HCl. Let's go with that one as aqueous, that one as gas, that one as aqueous. As long as it's not a liquid or a solid, we're fine. So, how do I balance it? It is actually. Okay, so here's how you'd write the equation. To find the Kc value, you would take the concentration of NH3. You'd use it once. You'd take the concentration of HCl. You'd also use it once. And you'd take the concentration of NH4Cl, and you'd use it once. And when you find that number, whatever it happens to be, if it's a large number, it means that you're making lots of products. If it's a very small number, it means you're not making a lot of products. Why would someone care? Okay, let's think back to the last lab we did. We made esters, right? What do you think the Kc value for your esters was? High or low? I'm going to say low. Here's why. When you were smelling your esters, could you still smell the carboxylic acids and alcohols? Yeah. You could, right? And you could smell some esters being made, right? But even if you looked at your beaker, you probably had a large amount of liquid on the bottom and just a small amount of ester on the top. Does that make sense? Because what was happening is your carboxylic acid and your alcohol, they were producing some ester, but the ester was actually returning right back to carboxylic acids and alcohols. But then it was returning back into esters again. But your percent yield was fairly low. Does that make sense? And this is why we heated it up, because by heating it up, we were trying to increase our percent yield just a little bit more. Because otherwise it's too low to be detectable. Does that make sense? So if we were to try to calculate the Kc value for our esters, it was probably like 0.03. Right? It was a pretty low amount. Right? If we could find a way to make our Kc value be like 10, 30, 40, 50, it means you're producing more product. It means that all we would have made was esters rather than having all of those reactants left over, which means that we would need to try to filter or try to like separate them using like a solubility or a funnel or a filter or a... Does that make sense? Okay. Boy, I sure have a lot of notes. Okay, can we do one last example? Okay, let's just do this one here and then we'll call it a day. So here we've got initial amounts of H2 and Cl2, and it's going to make HCl. That's basically the gist of the equation here. Well, according to our ice table, we should be able to throw some numbers in a certain spot. Both of these two things were at 576. So this guy right here is a 576. I'm just going to skip my units right now just to save some time, but don't be lazy. What's your HCl numbers? What should that be? Yeah, because you didn't start with any of it. Well, it only tells you one other number in this little preamble. It says that eventually the HCl is 335. So that means that at equilibrium it got to 356. How would this thing have got to 356? Well, it must have gone up by 356 to get there. Well, now I need to do something that I skipped earlier. I need to balance the equation. For one of these and one of these, you make two of these. Well, if this guy went up by 356, these two things here, they must have gone down. But they didn't go down by 356. They went down by half of that, yeah. So if someone can help me out, what's half of 356? 178? So it means this one went down by 178, and this one here also went down by 178. Because this 2 right here, for this number right here, and this 1 for this right here, is kind of your ratio. Your ratio matters only in the change column. So, what happens when we subtract these? Can someone else help me with that too? $398. Okay, so then for the last bit here, we want to try to calculate the Kc value. To calculate the Kc value, you take your product. We only have one of them, so that's the 356. And we put it to the power of its coefficient, which is 2. And then on the bottom, we put the 398 to the power of 1, and the other 398 also to the power of 1. If I could give some advice on how to put this in your calculator, I would do it like this. 0.356 squared. I would divide by 0.398, and then I'm going to press the divide by a second time, and also divide by the 398 a second time. I prefer to just do divide both times, because you have to take this number and divide by that one, and divide by that one. But you just got to make sure you don't mess that part up here. I got this value, 0.8. Okay, I promise, we're going to work with Kc values a lot more in the future, but as of right now, what does that tell you? Is this something that is driven more towards the products or the reactants? Reactants, yeah. Did you make some products? Sure, clearly you did. You made 356. So you made some HCl. Just like in your lab, did you make some esters? Without a doubt, you made some esters. However, there was also a lot of reactant left over. And if we had to compare the two, in this example right here, there is more reactant left over than there is product formed. The reason why the Kc value is important, though, is it's kind of unfair to compare these numbers to each other. Like, see these numbers right here compared to that number right there, because of 2 reasons. One, the coefficients make a difference. The recipe affects things, The other reason why is that there's 2 of these guys compared to 1. It wouldn't be fair to compare, like in a 2-on-1 fight. That's not fair to compare, you know what I mean? So that's what the KC value, that's what the KC formula tells you. So, okay, why don't we leave it there? I've got another really long lesson tomorrow, so I might start with one of these examples. Sorry, first couple of days of the unit are always really busy. I hope that made sense. Please bear with me. The first couple of days of equilibrium are kind of rough. It's kind of challenging to kind of mix both the theory and the math to it. So if that didn't make sense, please give me a couple more days before you freak out.